Okay. Okay, so here's the setting. The setting is going to be, we have a contact manifold with an exact symplectic filling, but I'm going to choose a particular example of this. So the example I'm going to choose is, so I'll write the contact manifold as V, but it's, I think for the purposes of this talk, it's always going to be a one-jet space. And it's going to have a symplectic filling, which I'll write as W, but W is always going to be half of the cotangent bundle of X cross R. So this is T star minus of X cross R, which is T star X cross R minus. Okay, but I will sort of draw this schematically like this. So here's W, and that goes off, and then the boundary of this is V. Okay, so some things will hold in more generality, but don't hold me to them. So I'm really going to assume this, I think, for this talk. Okay, so what is the motivation? So the motivation is there's this notion of a Fukaya category in this particular symplectic manifold, and maybe there's more than one notion of Fukaya category. So what I really mean is somehow the infinitesimal Fukaya category. By the way, some of these terms that I'm going to be saying, so A, I barely understand myself, and B, it's probably not necessary to follow, hopefully, the rest of the talk. So if I say things, there will be words that are just sort of for the experts, who hopefully will not feel that I'm abusing the notation too much. So there's this infinitesimally wrapped Fukaya category. So it's Fuk of W, and what is this thing sort of on an abstract level? So what it is it's built out of exact Lagrangians inside of W. So this is constructed from exact Lagrangians and W, and let's write L and W. So L will look something like this. And maybe there's some additional data that you need on the Lagrangians, which I will ignore. And also, I want to assume that if they have this non-compact end, that it's sort of cylindrical near there. Cylindrical near the end. So what that means is that as they approach this end here, that they approach a cylinder over some Legendrian lambda inside of V. Okay. That's correct. The Lagrangians, that's right. Yeah, I want them to be compact. And yeah. Yeah, I mean, they have boundary, but they should be. There shouldn't be any non-compactness inside of here, since indeed W is not actually compact. Okay. So the version that I'm thinking of, maybe in this particular setting, Nadler, I think, a while back. No?
Well, I mean, that's not an infinity category, what he constructed.
Yeah, I don't know. I mean, this has sort of a long and glorious history, and it came piece by piece, so I actually I'm not completely sure.
There was a student of Lenny Ng who maybe finished this construction.
Anybody know?
You guys know? Maybe you guys know? Elsa?
I'm not sure which student did the movie. I'm not sure which student did the movie. Is it Shield you're thinking?
What's that?
Shield?
No, Shield did something.
No,
Yeah.
some Odysseus.
Zach Silva? Is that the person?
Sylvain, maybe.
Zach Silva? I'm not sure he does quite this, but maybe it can be repackaged clearer and that I'm not seeing.
So I think this is what's called infinitesimally wrapped.
Yes.
Which is quite different from what's called partially wrapped, which is like submanifold.
And the infinitesimally wrapped.
Well, it's sort of one end of partially wrapped in some sense.
Do you guys know who actually finished it? So another thing is not really infinity from what I remember. But this was all the work of lambda, right?
Yes. Yes. Okay, I plead ignorance. Oh, no.
Okay, but let's forget about it. So let's continue. So we know what it is. But,
Certainly Nedler Zaslow, write this down at some point. But okay, anyway. Okay, so the goal is to construct something similar, but just using the end of this. So the goal is construct something similar. For just this contact n, which is v. Sure.
So I sort of understand it as a category associated to the fixed Legendrian boundary. So maybe I just ask, like, if you have two different Lagrangians with different Legendrian
Yes.
boundaries, how do those interact with this category?
So infinitesimally wrapped just means that you take one of them and you perturb it slightly, right? So if they're actually different, then perturbing it slightly doesn't actually do anything.
Okay, and so then it's just like the...
So it's just a regular. That's right. That's right. Okay. All right. So then maybe what I'll do is I will do a really lightning fast review of Legendrian contact homology, which I think you probably all know, or if you don't, then Baptiste's talk was probably a little bit mystifying. We have some Legendrian in this contact manifold, and so out of this you get a differential graded algebra. Right, so this differential graded algebra, the homology of this thing is called Legendrian contact homology, but the algebra itself, so A is the unital tensor algebra over, so I'm going to just pick some field and say that we're dealing with algebras over that field, generated by Rabe chords of lambda. And the differential, so this counts certain rigid holomorphic disks in the symplectization R cross V with boundary on the Lagrangian cylinder R cross lambda. And so I've tried to draw a picture of this here. So this is a picture that maps the 2-disk and its boundary in a holomorphic way into R cross V, R cross lambda. So here is this green, and I have no idea how well these colors show up, but this thing that looks to me to be green is the cylinder R cross lambda. And V is, I've drawn it a little bit curvy, and here's the R direction. Okay. So such a holomorphic disk, it has punctures on the boundary. The punctures go to Rabe chords at plus or minus infinity. And maybe I will write this as A1, A2. So this is an example where it has one end at plus infinity and two ends at minus infinity. But you could have, as you all know, any number of negative ends. Just the key thing is you have only one positive end. So this particular thing contributes to the differential of A, so it's some number, maybe it's somehow the count of this moduli space of things. So this particular thing would contribute a term A1, A2, and then maybe there are other holomorphic disks that give you other things. Okay. Okay. I think this you all know. So now let's suppose that we have an exact Lagrangian filling embedded of lambda. So this is exactly the picture that I drew up there. So out of this we get some sort of algebraic object on the DGA, and what it is it's an augmentation, right? So you get an augmentation, and now I've used both of the terms in the title of this conference, so I feel pretty good. So augmentation from A lambda to, let's say, your base field K. And so what does augmentation mean? So remember, this is an augmentation if when you compose it with the differential, so augmentation of A lambda D lambda. So sorry. epsilon from a lambda to k is an augmentation. There. Okay. So the way that this particular augmentation, this is an algebra map. The way that this particular augmentation is defined is it's defined on generators of the algebra. So I just have to tell you what epsilon L of a Rabe chord A is. And what it is you count holomorphic disks with one positive end at A and boundary on L. So maybe let me actually draw this. VW, here's L. And what we're doing is we're counting, that's the same color. Things that look like this. Okay. Great. Great. So instead of using Lagrangian fillings of lambda, what we'll do is we'll just look at lambda along with an augmentation. So instead of fillings, L of lambda, what we'll use is we'll substitute Legendrians with augmentations. So I'll write this as lambda epsilon. Okay. Great. Okay. So now, so those are going to be the objects in some sort of category. It'll be Legendrians equipped with augmentations. And now I want to tell you some further structure on this. So here's the setup. So the setup is, suppose we have a Legendrian link in V. So we have two disjoint Legendrians, lambda 1 and lambda 2. And let's suppose that we have augmentations on both of those things. Augmentations. So we can construct a linear complex. Linear complex. Okay, sorry. To construct a linear complex, so I'll write it as C12 with differential D on it. And what C12 is this is the just the vector space over K generated by Rabe chords from lambda 2 to lambda 1. So I'll write it like this. Oh, whoops. And now I should tell you what the differential is. And as I'm starting to write this up, what the differential is going to be for the experts is, I guess if you're an expert, you know this already. The differential will be the linearized differential for the DGA of the entire link, linearized with respect to the augmentation epsilon 1, epsilon 2, and restricted to this particular piece, C12, and then you take the adjoint of that. So I'll just draw this in pictures. So if I have two generators A and B of this complex, of the C12, so I want to tell you the coefficient of A in the differential of B. And what this does is this counts. Okay, now I need some more colors. So there's going to be holomorphic disks in the symplectization, and they will have, so they'll look sort of like the things that you count in Legendrian contact homology, except the boundary component will change. Okay, wait, so they count things that look like this. So this is what Baptiste would say. This is a contribution to the bilinearized differential, or co-differential. So I'm actually going from B to A. So what this is drawing is you have some holomorphic disk with some number of negative ends, and then these negative ends you apply epsilon 1 to this one, and epsilon 2 to those ones. And I'm going to schematically draw this. like this. So a, b with a plus and a minus. And then we have some number of punctures, which are minuses on here. And these ones, the ones on the left get augmented by epsilon1, and the ones on the right get augmented by epsilon2. And the colors match up. So this is lying on lambda 2, and this is lying on lambda 1. OK. OK, so so this is, to a Legendrian link, this is some complex, so a linear complex, it has a differential on it. So you can check that d squared is equal to 0, and you can use this to define the augmentation category. So the so far, I think everything that I've said that has any content is on firm footing. So this is where I start to get into things that we haven't quite checked everything yet. But OK, so so this is going to be a category that's associated to this context manifold V, which is a one-jet space, and this coefficient field K, which I'm going to start suppressing. So the objects, so this is actually going to be an A-infinity category, but let's start off with, so the objects are going to be Legendrians, lambda sitting inside of V with augmentations. Okay, and the morphisms, so if I have two objects, I'm supposed to find a morphism space between them. And what this is exactly this C12 space that I've written before. So this is just some vector space. And so far, this is just that vector space without the differential. So somehow this still, so hum spaces are equipped with a differential, which I've been writing as D. But maybe I'll now write this more suggestively as M1, and this goes from this hom space. So I'm also going to start suppressing the augmentations, because otherwise this is like, the notation is just too long. So it's going to be hom from lambda 1. This is going to be assumed to have an augmentation on it, and lambda 2 to itself. OK. OK. So I'm going to proceed with this in a second, but there is an obvious problem, and this is something that everybody, if you've thought about Fukaya categories, this is one of the standard problems, is that what if lambda 1 and lambda 2 aren't disjoint, right? So if they're not disjoint, so even worse, what if they're actually the same thing? But in particular, if they're not disjoint, then that thing doesn't quite make sense. So you have to do the standard thing also, which is to perturb them a little bit. I mean disjoint. Yeah. So if lambda 1 and lambda 2 aren't disjoint, then we just push one of them off of the other one by pushing in the Rabe direction. So the case that we're working with throughout this talk is the one jet space of X, right? So this is again T star X cross R, and let's say that Z is the coordinate in the R direction. So we just push lambda 1 slightly, so in the plus Z direction by just some tiny positive amount. And in general, this will make things disjoint. And this is sort of horribly non-generic. So maybe to make this generic, you have to do some further perturbation. So you have to perturb by maybe some Morse function on the Legendrian. So also plus perturb by Morse function. But again, this is sort of a statement of intent. So that this we can actually work out So it has been worked out explicitly for one-dimensional Legendrians, and we're working out the details in higher dimension. Okay. Okay. So what's the next?
Sorry.
Yes.
But this is not canonical at the chain level. Right?
This is not canonical at the chain level. That's right. But somehow the choices that you make maybe are in some contractible space. It's the usual. Yeah, there's a lot of pain involved in general.
But there is also in this, if you just do this, I mean, then you'll perturb again, maybe.
Yes. Yes.
Or maybe let you go.
Okay, great. Okay, thanks. So what's the next standard thing? So the next standard thing is that this M1 is just the first in a sequence of operations. In sequence of what are called A-infinity operations. So in general, they look like mk from hom lambda k plus 1, tensor down to hom lambda 1, lambda 2. So you just compose a bunch of these things together. Think of this as some sort of multiplication or composition operation to hom lambda 1, lambda k plus 1. And so these satisfy the A-infinity relations. And if I were actually to try to write down these, it would take me longer than I want to do, but let me just note the first one is m1 squared is 0, and the next one is that m1 composed with m2 is equal to m2 m1 tensor the identity. Where's the plus or minus? Okay, there's some sequence of relations that they satisfy. So I will maybe draw for you how you define M2. So I've drawn how you define M1. So I'll draw M2, and then you can use your imagination to figure out what happens after that. So here's something that contributes to M2 of BC. So this is going to be A plus stuff. So here A goes from, let me just draw schematically. So A goes from lambda 1 to lambda 2. So it's in hom lambda 1, lambda 2. B goes from lambda 2, lambda 3. And C goes, oh no. Sorry. B, C, A. So the M2 operation for B and C, I got this backwards, didn't I? CB. Lambda 1, lambda 2, right? Yeah, okay. Stephen knows that we spent a long time agonizing on this idiotic point. Okay, so what this does is this counts something similar to, this thing is like a bygone, so this is going to be a triangle. This is lambda 1, lambda 2, and let's see if this looks different. Yeah. A, C, nope, B, C. And there could be some number of, so this is a positive puncture here, negative corners there, and possibly some number of other negative, auxiliary negative corners, but anything that otherwise is here is augmented away just like over there. So this is epsilon 1, epsilon 1, epsilon 2, epsilon 3, epsilon 3. Okay, so this is still all sort of stuff that you can get from just the general framework of Legendrian contact homology. That's just that now we have a link instead of just a single component thing. Okay. And the reason, by the way, that the A-infinity operations are satisfied is essentially just because d squared is always equal to 0 even when you have multiple components. You just sort of write that out. Okay. So again, we have this issue that if some of the lambdas are, these inputs are not, some of the lambdas are not disjoint from each other, then you have to do something. And so what you do is you perturb them, but the ones that are earlier on in the sequence you perturb by a little bit more. So if lambda 1, lambda 2, lambda 3 aren't disjoint, or even if they are, we perturb, so push lambda 1 and lambda 2 in the plus z direction by, so lambda 1 I want to push by the most, so maybe 2 epsilon and epsilon respectively.
I have a little question there. So suppose you have just one lambda.
Yes,
And so you push lambda to lambda epsilon by a little bit.
that's right.
And then maybe you need another one to get
That's
lambda
right.
epsilon to lambda 2 epsilon.
That's right.
Now when you write this M2, it's gonna go from lambda epsilon tensor lambda epsilon lambda 2 epsilon
Mm-hmm.
into lambda 2 epsilon.
Yes, and not lambda epsilon, or not.
Right, and so why does this give you an infinity structure?
Yeah, so this is not so, it's not so clear, so you have to, there's something to check. So in one dimension, this is something that we read out in our paper. This is consistent sequences of DGAs. And in general, we're still sort of working it out. But this is somehow, yeah, so this is one of those standard problems.
This is why Nadler's construction was not an infinity category.
Right,
That's
right.
exactly the point where we're getting a structure that's called maybe a pre-infinity category.
That's right. So there you have to make some choices, and you have to make them sort of consistently. So you can choose, you can place a Morse function on each of the Legendrians, but then you need something further to perturb a little bit. So you have to put in some additional data, and then yeah. No, but that's completely right. So there are some serious technical issues to solve here, but we think we know how to do it. But again, this is still work in progress.
You need them to be disjoint so you can only jump from one to another at a rate point.
That's right. Well, the DGA doesn't work so well when you have just an immersed Legendrian is the deal. And so that's what would happen if you actually have intersections. Okay. Okay, where am I? So here's the proposition in this setting where, again, maybe I'll say this one last time and then stop beating you over the head with it. So V is supposed to be a contact manifold that's a one-jet space. So aug of V, this is an A infinity category, a unital A infinity category. Okay. And if you don't like A infinity categories, but you're okay with regular categories, then the usual note here is that if you take the cohomology category that's associated to this, so note, then the cohomology category H star of aug of V. This is an honest category, unital category. So I guess that this is actually a strictly unital A infinity category. The cohomology category is an honest unital category where the homs in this cohomology category is H star hom in the augmentation category, and composition is M2. Okay. Okay, so this is very similar to things that have been defined in the past. So this is so suppose that now we fix a Legendrian. So far this you can choose any Legendrian and any augmentation, and that will give you an object here. But now we're going to fix a particular Legendrian lambda. Okay, so then the augmentation category of lambda, which I'll write as aug of lambda, and which we wrote as aug plus of lambda before. So this is the full subcategory. It's essentially just take this category, but restricts to objects where the Legendrian is lambda. So the augmentation can vary, but the object is always lambda. So this is a full subcategory of aug of v corresponding to objects lambda with any augmentation on them. So any epsilon. I'm going to start using terms like full subcategory more. So again, this is just take this construction that I described here, but restrict yourself to just things where the Legendrian is one particular fixed one. Okay. So this is also a unital A infinity category, and this is what was described by this joint work, and this is really following construction was essentially given by Bourgeois and Chantrin. Okay. And maybe I will just say out loud, but not write down, that if you have an object in this category that's this Legendrian lambda along with an augmentation that comes from a filling, then and you take the self-hom of that with itself, what you get is you get the the usual chain complex, Morse complex for the cohomology of the filling. So H star of self-homs is just H star of filling. I'm going to say that maybe again, so I won't write it down right now. Okay. Okay. So the next thing I want to do is I want to talk about how you can derive this category. So this will be a derived version. Augmentation category. And this is all going to describe a standard setup, but maybe I'll just write down some of the key points for you, and either you've seen these sorts of things before, and then what I'm about to say will bore you, or you haven't seen it before, and this I'll try to, at least, there's no way I can sort of give you full details, but I'll try to guide you through it. So the first thing we do is we introduce a category which is the category of twisted complexes. So this is an A infinity category. I'm going to define a category of twisted complexes on this. So objects are twisted complexes. So what is this? So I can take a bunch of objects inside of this category. So those look like lambda 1, epsilon 1, lambda 2, epsilon 2, etc. through lambda n, epsilon n. And then what a twisted complex is it's just a choice of an element of hom in the arrows that I've just drawn right here. So you have an element of hom lambda 1, lambda 2, element of hom lambda 2, lambda 3, etc. up through n. But then there are also ones that sort of jump steps. So it's basically any possible arrow you can draw from the left to the right. Okay, so you have an element. So you have an element of hom, which you can think of as just a map of each of these things. So twisted complexes of objects in aug v, subject to certain compatibility relations, which I don't want to write down, and I actually probably couldn't on the spot. I have to think a little bit about it. Okay, but the good news is that actually, in this particular setting, I can tell you, sorry about the glare, I can tell you what a twisted complex is in our setting. So proposition, by the way, this is like by far the easiest of the propositions I'm writing down. So this one is maybe, it deserves to be demoted a little bit, but anyway, okay. So twisted complexes, so objects of this thing, are exactly in one-to-one correspondence with links you might have to perturb the links a little bit. Lambda 1 through lambda n. So that's just a twisted complex. You just take the union of these Legendrians, and that gives you some link, and then possibly you have to perturb it a little bit as before. With what's called an upper triangular augmentation. So this is an augmentation of the DGA for this entire link right here, but the only things that can possibly be augmented to something non-zero are Rabe chords that go to something here from something to its right, or itself. So what this means is that epsilon of a Rabe chord to lambda I from lambda j is equal to 0 unless I is less than or equal to j. Okay, so this is an augmentation. So this twisted thing seems a little bit scary, but it's really just an augmentation of this link, but it's one where you can't augment things that go to something over here from something to its left. Okay, and in particular, if you just restrict to these pure Rabe chords from a link component to itself, then you get these augmentations epsilon 1 through epsilon n. Okay. So let me give an example of this, because I think this is sort of a nice sort of fun thing. That there's a lot of theory behind this, but somehow it becomes something not so bad. So here is two Legendrians, so lambda 1 and lambda 2. So these are front diagrams in R3. So this is x is equal to r. So this is just Legendrians in R3. And I've actually drawn these two things so that they do overlap a little bit. Okay, so before I do anything else, I'm supposed to perturb these things. So I perturb them slightly. I push lambda 1 slightly above lambda 2. That's actually still not quite generic, so I have to. Let's see if I can do this. Above. So I push lambda 1 above lambda 2 a little bit, but then I also perturb a little bit along this segment where they overlap, so that there's just one Rabe chord in there. The way, if you just push it up directly, then there will be a whole family of Rabe chords. But I've set it up so there's just one in here, which I will call A. And there's an augmentation of this particular Legendrian link so that epsilon of A is equal to 1. And I think everything else, all the other Rabe chords get sent to 0. There are only 4 total Rabe chords, if I've drawn this correctly. And so this would correspond to such a twisted complex. So this is an augmentation where this gets sent to 1, everything else gets sent to 0. And this gives me something that I'd write like this. This corresponds to the twisted complex. Lambda 1 goes to lambda 2 with the element A in hom of lambda 1, lambda 2. Okay.
Can I ask about upper triangular augmentations?
Sure.
Are those graded?
Yeah, so everything inside is supposed to be graded. Do you have to shift? Yeah, so you have to choose Maslov potentials and everything. So,
Okay, so there's also like formal
there's also, that's it, yeah. Yep. That question shows that people are paying closer attention than I was hoping. Okay. Okay, so that's an example of a twisted complex. Sort of a two-term complex. Okay, and so if you take if there's an A infinity category whose objects are these twisted complexes, and there are A infinity operations on them, which I won't describe, but when you take all this together, you get twisted complexes for A and aug of V. So this is an infinity category. So again, I haven't defined what, I've told you what the objects are. I haven't told you what the morphisms or anything else is, but you can sort of deduce it from general nonsense. And out of this, there's this notion of what's called the derived category. Maybe I'll write it down here. I'll write this as D aug of V. And what this is this is the cohomology category of the category of twisted complexes with the first A infinity operation M1 on this. So this is a real mouthful. Let me just say that this is some sort of category. This is an honest category whose objects are twisted complexes. Okay, so the objects are the same as the objects in this twisted category, but the morphisms are a little bit different, but I'm not going to get into those. So this, again, let's just think of this, either you know what this is, or this is, think of this as a black box where you have some category whose objects are these twisted things. Okay. Excellent question. Yes? Question mark.
I mean, so you like looking at the full category generated things.
So what we can, yeah, exactly. So we can show that it's actually generated by objects that are isotopic to the unknot. Is that is? That's not the same as finite generation, but where's Baptiste? So Baptiste says yes.
Well, or to maybe ask it more geometrically, like if you look at the full subcategory of everything isotopic to the unknot, then even like as morphisms, you have kind of all possible two-component links.
Yes, that's probably not enough. So you need to have complexes, longer complexes.
But so that's already.
That's enough. Yeah. Oh, that is the part that I don't know, but maybe we believe is true. Okay. So the statement that I can say is that this is generated by that full subcategory you just described. Okay. And I will try to say that in a little bit.
Do you have any hopes of this being like fairly combinatorial in dimension 3?
It depends on your definition of fairly, I think. So, I mean, it is in some sense completely combinatorial. Yeah, maybe I'm actually going to lead up to an example that, yeah, okay. The example probably will not clarify anything, but it'll make me feel better. Okay, so following work of Nadler, here's a definition. This definition is going to seem a little bit weird as well. So suppose that we have some twisted complex, which I'll now write as A. So this is something, it's an object in this derived category. So the rank of A at a point inside of V. So if you have a point inside of your contact manifold V, the rank is the rank of hom in this derived augmentation category. So this is going to be completely baffling, probably, or at least it is to me. So it's the rank of the hom space in this derived category from U to A, where what is U? So U is a small unknots around P. So in this particular case that I drew there, you can look at, for instance, so it's the rank along this entire bit right here, it's always 1. And then here it turns out the rank is 0. So intuitively, the way I think of rank is it's sort of a multiplicity of this link, or this sort of Legendrian that's a whole bunch of Legendrians. It's a multiplicity at a particular point. But somehow there are two bits of the Legendrians that are going through this, and they overlap, but they somehow cancel each other out. So here, yeah, you have to orient everything. That's right. Yeah. The rank there is 0. The rank here is 1. Maybe I should draw it. Oh, that looks about the same.
What is A and what is P on the picture?
So P is this point here. A is this complex that I drew up here. Yeah. And so a little unknot would look something like, at this point P, it would look sort of like, I can't draw it, but something like that. So this is really imprecise. Also, this is even as an obscure definition, this is sort of imprecise. So you have to make it more precise. But maybe I won't do that. So think of this as sort of multiplicity at a point. It's actually sort of surprisingly hard to calculate, or at least for me to get an intuitive sense for how to calculate this. But in this particular case, yeah. So the rank is 1 along here. The rank is 0 everywhere else, including along there. So here's the definition. So now we have a fixed Legendrian inside of V. So then we can define a subcategory of this. So I'll write as d aug lambda V. So this is the full subcategory of d aug V of objects with rank 1 on lambda and 0 otherwise. Okay, so in this particular case, if I draw that thing that's right there, and I call that lambda, so this particular twisted complex, lambda 1 to lambda 2 A, this is in d aug lambda V. Okay, and now I can unveil this thing that I drew before the talk. So here's an example of a twisted complex, also just lambda 1 to lambda 2 with some map in between them. So lambda 1 and lambda 2 here are both unknots. Here's lambda 1, and here's lambda 2. And you see that they overlap on this little thing right here. Well, it turns out that the rank of this twisted complex, so what exactly is this complex? So there's, again, you perturb sort of like before, and right in this overlap region, you perturb it, so there's one Rabe chord in there. And that one Rabe chord we augment, and so we get something that looks like this. So this particular twisted complex, if you calculate the rank at any point, it turns out it's 1 where the multiplicity is 1, and along this sort of common region right here, it's 0. And so if I were to draw this thing except minus this common region, I get this picture right here. And this is a Legendrian knot lambda, and so this particular twisted complex is in d aug lambda V.
So is it true that if you take any A like this and you look at this locus where the rank is 1, you see a front or you see a wrong?
So in general, you might see an immersed Legendrian graph. But indeed, it's some sort of singular Legendrian. But there will be particular complexes where the Legendrian that you get out of this thing right here actually is an embedded Legendrian, and so that gives you this subcategory. Okay. Now, of course, I've used up that board. Let's see. So in fact, in this particular example, well, let's see if I can squeeze it right here. Shifted up, yep. Yeah, in fact, this doesn't work if you interchange these two things. So in fact, for this particular example that I have here, lambda 1, a lambda 2, this particular twisted complex, in this derived category, this is actually the same thing as a complex with just one thing in it, which is just lambda with its unique augmentation. So it turns out that there's unique augmentation on lambda. And so this twisted complex right here, which is, again, I've started omitting the augmentations, but this is lambda 1 with its unique augmentation, lambda 2 with its unique augmentation, some sort of complex like this. This is isomorphic to this in the derived category. Right. So this twisted complex, you actually don't, in this particular case, you don't need to take a twisted complex. It's isomorphic to something where it's just lambda with a single augmentation on it. Okay. Okay, so maybe I can write up. So what you notice in this case right here is that we have this Legendrian. So you can work this backwards. So you have this Legendrian with an augmentation on it, and that thing. This is some famous example of an augmentation that doesn't come from a filling. So you can sort of check by topological reasons that there's no embedded filling that gives this augmentation. But it does come from, it's isomorphic to a complex of things that do come from fillings. So we have lambda 1 and lambda 2 are both unknots, and their augmentations do come from fillings. So you can actually make this more general. So so this derived category is generated by, this is what I was trying to say, but sort of less precisely before. So this is all unknots. And for each unknot, there's a unique augmentation coming from a filling. And so this is some sense in which, so all augmentations come from filling. So again, it's not the case that all augmentations of any Legendrian knot come from fillings, but in this one jet circumstance, they all come from fillings. In fact, fillings of the unknot, but in this sort of derived sense. So of the unknot.
What's V here?
What is V? Oh, V is the contact manifold. The V is one. V is always a one jet space.
So it's R3.
In this case, it's R3. Yeah. Right. Yeah, I think we make no claim about more general contact manifolds. So I've now left myself with a little bit of time to tell you where this proposition comes from and sort of what the big picture is. So this is all sort of some, at least to me, fairly daunting thing. Let me try to place it in context. So the big picture. So to get to the big picture, let me go back to this picture that I drew at the beginning. So we have a contact manifold V with a filling W and a Legendrian lambda with a filling L. So I mentioned this infinitesimally wrapped Fukaya category for W, which is generated by these sorts of exact Lagrangians. So you can take a derived version of this. So this is the derived Fukaya category. For W. And again, you have to mumble something, infinitesimally wrapped something. And there's, so again, if you have a Legendrian lambda inside of V, then we get some full subcategory in here that I'll write as d Fuk lambda of W. This is a subcategory that's generated by, well, the way to say it is that you just look at Lagrangians that are cylindrical to lambda at the end. So. cylindrical to lambda. Okay, so they're asymptotic to lambda at the ends. Okay. So here's a proposition. So the proposition is that there is a functor, and in fact it's fully faithful, from the derived Fukaya category to, to the derived augmentation category. So this is just supposed to say that well, if you have an exact Lagrangian filling of some Legendrian, then you get an augmentation over here. And this is just some derived version of this. So there's, you get a functor from here to there. Checking it's fully faithful requires some work, and maybe possibly, in this case, you can use Baptiste's work on Dulu. But you need the entire thing, right? You need the infinity.
Yeah, Dulu doesn't get.
Oh, that's true.
Yeah.
Okay.
Not yet.
Okay, so maybe I will say no more about that then. Okay, so there's some sort of fully faithful functor that goes like this. And then let me just say, let's see, I'm going to take a couple more minutes. So there's work of Shende, Truman, and Zaslow where if you have this Legendrian inside of a one-jet space, there's some sort of sheaf category. So I'll write as SH lambda of x cross r. So this is lambda in J1 of x. You get some sort of sheaf category of constructible sheaves on x cross r with micro support on lambda. I'm really not going to try to define any of that, but this is some sort of category. And then there's this is a little bit of work in progress that there exists a fully faithful functor. So why am I bringing up this thing? Hopefully this will make sense in a second. So there's a fully faithful functor from this derived category to this sheaf category. So this is some sort of functor from an augmentation category to a sheaf category, which again I probably will not talk about. But now you can try to combine these two things, and what you end up with is, so you get, so. So you have some composition like this. Each of those arrows is fully faithful, and it turns out that the composition of these things is something that people already know about. This is the Nadler-Zaslow functor. And this is known to be an equivalence. And because these two maps are fully faithful, that means that each of these two things is also an equivalence. So that means that the map from augmentations to sheaves is an equivalence. And there's a further conjecture that this derived category is actually the same thing as just the augmentation category of lambda. And if you put that together with this, so that is the part that we haven't quite figured out yet, but have some ideas on how to get. And if that's the case, you can replace this by just the augmentation category of lambda. And this says that the augmentation category of lambda is equivalent to the sheaf category, which is a result that we proved in NRSSZ for the case of R3. But this is sort of do it in more generality.
Your sheaf category, are those rank 1 sheaf?
Micro-local rank 1, yeah. Okay, so I think that's probably a good place to stop, and thanks.